Okay, welcome back. We're talking about the KMP sorting, not sorting, KMP searching algorithm, and building this fail array. I mean, yeah, you're going to have to build a character array the size of the substring. So you could say it has some space complexity issues, but clearly not much, right? I mean, if I've got a Word document that's 5,000 words long and I'm hunting for a four-letter word, having having an array that has four letters in it. Okay, fine, whatever, dude. I mean, yes, it does have some space complexity, but certainly not much. Okay, so you got to admit, building this fail pattern is a little complex, and the way to kind of do it is by this little visualization. Here they deliberately have one with a bunch of duplicates. So if I fail here, well, then I can start all the way over. But I can't, if I fail at this location, then the next thing could start with an A. So I can go back to A. Here, there is no other things that start, so I have to go back to A. Anyway, I know this is difficult to see, so just bear with me. This is how it works. Okay, so the algorithm on page 216 and 217 is kind of minimalistic. Yeah, that's what it looks like, right? And then here's how you calculate the fail array. So what did it do for me? So the analysis here is, how much faster is this? Well, it kind of sort of depends. If, for example, there were no duplicate patterns, no like AB, AB, right, in the thing you're looking for, then the ability to scoot forward is kind of thwarted. So sometimes the pattern is going to be absolutely identical to the performance of the other technique. And then sometimes it's going to be much, much better by reducing the number of comparisons because you skewed it over. Now, the number of character comparisons is the same. It's just instead of taking, like in the example at the very beginning, so the number of character comparisons is the same, except instead of taking 7 times to get there, I can get there in 4. So, yes, okay? The worst case is going to be identical to this, all right? So not that much difference. So the reality of it is that the length of the text, if you were to calculate this out, it's really not going to be that much different if you're just using the big O notation. It's still going to look like that. Now, is it better? Yes. Is it an awful lot better? Yeah. Okay. It's a lot better. So what's the real world experience? Depending on what you're looking for, we're talking about relatively minor speed improvement, comparison improvement, like, maybe 12% maybe. Not a huge amount of performance increase, because it just, the average case is just so doggone difficult to calculate, because I have to know, the length of the thing I'm looking for plus the length of the thing, and now I need to figure out, does it have any repeating patterns in it? So it's like, geez. So rather than try to calculate the average, which would be practically impossible, we can just compare the big O notations and say, this one's better than that one, but still it's on the scale of the size of the text times the size of the string. Okay. Now, this one does have a little bit of initial overhead, right? You have to build that fail array. I mean, it's not very much, but a little bit overhead. So if the thing you're looking for is rather short, the longer the string is, the probably a little bit more performance comparison you'd get out of this. The KMP would be a little bit better if the substring was a little bit longer, those kinds of things. For that matter, even if the text was longer, because you're reducing the likelihood of getting more skips. Okay. So that technique is pretty doggone cool, but it's really not the end all. The end all is just another one called Boyer-Moore on page 218. And so somebody spent an awful lot of time on this and figured out that if you were to compare, instead of comparing the letters from front to back, you could compare them back to front. Well, let me get back to this guy. I thought I had a graphic of that. Doggone it. I hate that. And I can't find the graphic. Instead of starting with T and H and E, you start here. Y. Does Y equal R? No. Boom. Okay, that's an improvement right there. I only have to do one comparison to find out whether, in this scenario, one comparison to find out that I'm not there. Now, oddly enough, the English language has an awful lot of things at the beginning of the word that are the same, and fewer things at the end that are the same. There's some example, maybe like, the plurals and things start with end with an S might be an exception to the rule, but somebody figured out that if you started with the back of the word versus the front of the word, you'll have more opportunity for skips. And apparently they are correct. Okay, so Boyer-Moore starts from back to front, and then figure 7.4, if I can find figure 7.4. I don't have figure 7.4. Okay, so figure 7.4 basically is this guy over again. And just starts a different location. Okay, so this one, instead of having, remember we had a fail pattern, but it really wasn't a fail pattern. This one really does have a fail pattern, and I said that wrong. It has a success pattern and a fail pattern, except the success pattern really wasn't a pattern, it just moved over one. This one used two pre-processed things. One for what they call the good character slide, which means, ooh, we're getting close. We can scoot over some. And how far do you want to scoot over? Because if I had AA and I ran across an A, I could scoot over 2, right? Okay, good. And then there's a bad character slide, and then a good character jump. I know these terms are kind of weird. And jumping is relative to itself. Like if it was an ABC and an ABC, I found the first one, but now I can say, screw that, I'm going to jump over. Doink! Move over to the second half of this guy because I know the first half matched. So the second half is, because I know the first half matched, I know darn well the second half of that pattern is going to equally match, right? Okay, good. So here, there's some rules on how this thing's supposed to work. They have, if we have a mismatch, we use knowledge of the mismatched text character to skip over. That's what's called the bad character slide. If we match some characters, but not all, then we use knowledge of the matched characters to skip the alignment called the good suffix jump. Okay, so it's just taking the KMP and kind of sort of doing a little better job by figuring out, aha, I have an opportunity to move over an awful lot, or I have an opportunity, I found something, and I know, since I know the A match, well, shoot, I don't even have to check to see if the second A matched because I know it did. That kind of thing. So generally speaking, this is considered the best technique. By the way, there are hundreds of string pattern matching algorithms out there. We're only using 3 of them, the standard so-called naive technique, the KMP, and the BM version. That's it. That's all we're using. So yes, it does have some space complexity because I'm now building 2 sets of arrays, and it has some overhead. And then if you were to do the math on this guy, the site would be something like t squared. If I can get the keys to work. That's essentially what the big O notation would come out to. Now, in the way it works here is basically people who've studied this, if the thing you're looking for is about 6 characters long, this one has some pretty decent performance increases. Under 6 characters, not so much. So let's just go look at the algorithm. And the beginning algorithm doesn't look that bad, okay? But wait till you get to how to calculate the slide and jump arrays. Okay, so let me finally get back to where the heck I'm supposed to be. Okay, so here's how we start off with the algorithm on page 220, where I have the length of the pattern, this part looks the same, right? No problem here, except now I say, when it comes time to sliding over, I want the maximum of either the slide for that guy or the jump for that guy. In other words, I'm scooting over because I failed miserably, or I scooted over because I don't need to calculate that thing over a second time. Either way, see? So this one has a jump on good things, because I've already calculated that. I know A is going to match A's. Don't need to check it a second time. And the very same thing I've missed horribly, so I could scoot over 4. So the fail array is actually roughly the same, except now the success array, the slide guy, is a lot more complicated. Okay, and then all the rest looks the same, doesn't it? So it's just a matter of doing the slide and jump. Okay, let's go look at the slide and the jump. Okay, so here we go. Here's the slide array. So the slide array basically says, I go through here on every character in the array. In other words, A, B, C, D, that kind of stuff, right? And then basically I put where that thing appears in this array. So this is a fairly decent size array that I'm building, because it's one for the entire character set. And then I go through this guy and set it up so that I know if there's duplicates, what's the distance between the duplicates. So, I'm looking for L-I-T-T-L-E, and then there's another L over here. Well, then, what's the difference between this L and that L? Okay, that's how that part works. So this one is not bad, but let's go look at the fail array. Holy moly, that's a heck of a lot of work just to produce the array that I'm using. Wow. That is an awful lot of stuff. An awful lot of stuff. Let's go look at a real implementation. So first, this is the KPM technique. So it looks roughly the same. I have a routine here that builds the fail array remember the KPM really doesn't have a successive guy. And so this is the fail guy. It's not that complicated, right? Now here's the BM method. And BM probably stands for lots of things here. So I get the slide array, and then I get the jump array. Now remember, the slide array doesn't look that bad. So here's the slide array. So since I'm using 8-bit characters, I'm going to assume that this guy, I'm assuming that my characters are 8-bit. So 256 characters in this thing, in this slide array. And then I go through and I populate them with each one of these things. Start off with the length, starts with, 5, because that's the length of the word little I'm looking for, right? So every single one of these gets 5 in it. And then I go through and actually calculate the difference between that one and the next one, that one and the next one, that one and the next one, that one and the next one. So this slide pattern starts off with 5. If Z is not in there, it's going to skip to 5. But if A is in there, but in the second position, am I going to skip? What am I going to skip? Well, see? Okay. And then the jump array. This one is very complex. You have to go through an awful lot of stuff. It starts off with basically a pattern, and then you go back and tweak it, and then you go back and tweak it a second time. And so there's a heck of a lot of overhead on this guy. So how much better is this one than the other two techniques? Well, it is better, and quite frankly, the BM method is considered the standard technique. I would imagine, for example, in C#, if you were to look at the index of, it probably is using the Boyer-Moore, or maybe it looks at the size of the thing you're looking for and then chooses between KMP and BM, maybe. Okay, we're coming up on the 15-minute mark.